Alright, so in this video, we will be looking quickly at how to figure out if an element or an ion is paramagnetic or diamagnetic. And we do so simply by using our electron configuration and a simple rule about unpaired electrons. So we can figure out whether something is paramagnetic or diamagnetic. And so what you're going to want to remember here, the key distinction is when we're looking at something that is paramagnetic, it's going to have unpaired electrons versus a diamagnetic atom or ion. There, all the electrons are going to be paired. It's as simple as that, really. And so how exactly are we going to figure out whether we have an atom or ion that has paired electrons or unpaired electrons? Well, we're going to have to use our electron configuration as well as something known as an orbital diagram. So let's start with an example. Let's say we want to find the electron, we want to figure out whether oxygen is paramagnetic or diamagnetic. So let's start by finding out the electron configuration. I assume by this point you are comfortable finding electron configurations out by yourself. If not, I've made other videos on that in the past, so be sure to check those out. But in any case, let's say that we're trying to find the electron configuration of oxygen. We know that it has 8 electrons, and so let's figure out the electron configuration for oxygen. That is going to be 1s2, 2s2, 2p4. That is 2 plus 2 plus 4 is 8, so we've accounted for all 8 electrons. This here is our electron configuration. And so now we're going to want to find the orbital diagram and we're going to want to draw out the orbital diagram. And so, well, what is an orbital diagram? It's simply going to be a visual representation of how the electrons are distributed in their orbitals. They're going to show those different energy levels, sublevels, the s, p, d, f, as well as electron spin. So it's just a more detailed version of an electron configuration, really. And so instead of just writing out the subshells, we actually show the orbitals using lines and then arrows in order to represent the electrons. And so each electron is going to be represented using either an up arrow or a down arrow to denote the spin. So this is a spin up and this is spin down. But each of these just represents an electron. Okay, so in our case of oxygen, we're going to have a 1s, 2s, and then there are always going to be 3 orbitals for the p, right? There's 3 p orbitals. So there's 1s orbital, there's 2s orbitals, and there's going to be 3 orbitals that make up the 2p sublevel here. And so there's a couple of rules that you're going to want to follow that are based on certain scientific principles, and that I'm going to actually detail in another video dedicated directly to orbital diagrams. But in this case, we can just simply see what is applicable here. So we can see that in our electron configuration, the s orbital here, 1s has 2 electrons, the 2s has 2 electrons, and the 2p has 4 electrons. So now we're going to just draw this out using the arrow notation for our electrons. So we'll start by drawing out the 2 electrons in the 1s sublevel. And what's important to note is that you have to fill out the electrons with opposite spins. So if one of them is facing up, the other has to face down. That's just one of the rules you need to know. And you also go from lower energy, that is 1s, and upwards. So this is the direction that you fill up. You start with the lower ones and then you move up. You can't start from the top. So this is 1s, 2, 2s, 2. And then once we get to the 2p, we can see that there are actually 3 orbitals, but all 3 of these orbitals have the same energy level. And so when you have orbitals that have the same energy level like this, they're called degenerate orbitals. Degenerate orbitals. And so when we're dealing with degenerate orbitals, the way that we fill this up is actually a bit different than what we're doing here. We wouldn't actually just go with our up, down, and so on. Rather, what you're going to want to do is you're going to want to move across, adding 1 electron at a time to each of these orbitals, ensuring that you have parallel spin. And what that means is, let me just demonstrate. The way that you would fill this up correctly is you would add an up electron, then an electron with up spin, and an electron with up spin. So all electrons here, you're going to fill up having the same spin. It's called parallel spin. And then if you have, once you do that, once you add an electron to each of the orbitals, if you still have more electrons to add, you would go back and then go down, 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 in that sort of fashion. And so in this case, we can see that our 2p sublevel here only has 4 electrons, so we would go parallel spins, 1, 2, 3, and then 4. And so this is going to be our orbital diagram for oxygen. And from this itself, we can see that here, okay, we have paired electrons. Their electrons here are paired. This is paired, but here we see we have unpaired electrons in this 2p sublevel. And we remember, if we have unpaired electrons, well, that means that we are looking at an atom, or ion, in this case, an atom, that is paramagnetic. Paramagnetic. It is that simple, and this here is going to be our answer. All right, now let's just look at a couple more examples of this idea. So we've now found found out whether oxygen is paramagnetic or diamagnetic. Let's move on to see if neon. Let's see if neon is paramagnetic or diamagnetic. So neon is over here. So if you remember, we start out by writing out our electron configuration. And so we can see neon has an atomic number of 10, so there's going to be 10 electrons. And so our neon will have an electron configuration of 1s2. Let's write this neater. 1s2, 2s2, 2p6. This is our electron configuration. So now we can move on to drawing out our orbital diagram. So again, we will have a 1s, 2s, and then 3, 2p, 2p. All right. We can now fill up these orbitals. Remember, following the rules that we did before, 1s2, 2s2, and we fill this out again using the proper method, which is parallel spins, 1, 2, 3. We still have to fill out more, so we come back and opposite there. So this here is our orbital diagram. And from this, we can see that all the electrons are paired, and since we have all electrons being paired, this is going to be diamagnetic. There is our answer. So yeah, pretty straightforward. It's a quick trick, quick method to figuring this out. All right, let's look at another example. Let's say we want to find out an ion. Let's just do an ion for example purposes. Let's say we want to figure out whether the Fe3+ ion is diamagnetic or paramagnetic. Well, our iron 3, the atomic number is going to be 26, right? Or our iron has an atomic number of 26. And we remember that this is an ion that we're dealing with. It has a +3 charge. And so instead of the 26 electrons here, this is going to be 26 minus 3 electrons for a total of 23 electrons here. And so we're going to start by writing out our electron configuration. And since we have previously learned this, we can see that since we're dealing with a lot over here, let's just start out with our noble gas configuration and write this as Ar 4s2 3d6. Again, in case you haven't seen the video on noble gas configuration, that I've explained pretty simply what this means, but again, just for clarity purposes, I guess I can just write it out. 1s2, 2s2, 2p6, 3s2, 3p6. That brings us here. 4s2, 3d6. So this is our electron configuration, and now we can draw out our orbital diagram. But before we actually do that, you'll notice that this is, I forgot to mention, this is actually not the electron configuration for the iron 3 plus ion. Rather, this is the ground state iron atoms electron configuration, or the the iron neutral iron atoms electron configuration. If you'll remember that, as we mentioned here, we are losing 3 electrons. And so where do these 3 electrons come from? Well, we have to start by removing the electrons from the higher energy and then downwards. So rather, we would not actually end up with, if we're looking at the end, 4s2, 3d3, we would not remove the 3 electrons from the 3d sublevel. Rather, though we write the 3d after, the 4s sublevel is actually that of higher energy. And so what we would end up doing is, from our 4s, we would end up taking away 2 electrons, and from the 3d, we would end up taking away 1 electron for a total of 3. And so what we would end up getting here would be our 4s0, right? We take away 2, so it's 4s0, 3d5. 4s0, 3d5. And that is what we're going to be using when we now draw our orbital diagram. So to draw out the orbital diagram here, let us start, again, as we did before, with our 1s, followed by 2s, 2p, then, here, let me draw this, it's better, 2p, 3s, 3p, 4s, and then 1, 2, 3, 4, 5 for our 3d. And so we would then move up the ranks as we did previously in order to fill this up. So we can see that we have 23 electrons, so let's just count and move our way up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Again, there's nothing in the 4s, right? 19, 20, 21, 22, 23. And that gives us 23, and we can see again, while all of these are paired, we do have 5 electrons here that are unpaired. And so, because we have unpaired electrons here, that tells us that our iron 3 plus ion is highly paramagnetic. Magnetic. Oops. And that is going to be our answer. So that brings us to the end of this video. Hopefully that made some sense. And again, drawing orbital diagrams is not too hard, but it just takes some getting used to. But in any case, if you found this video helpful, please show your support by liking, subscribing, and comment what you'd like to see next. And I will see you guys in the next video.